All right, welcome everybody. Today we're going to continue on with this idea of a moment, but this is going to be a little different because up to this point, what we've been talking about when we say a moment is a force times some kind of lever arm, or a force times a distance. We did moment about a point, we did moment about a line. This one is going to be moment of a couple. And basically what the couple is two forces, and I have it already drawn here. Two forces that are equal in opposite directions separated by a distance. So let me go ahead and jot that definition down. Bam, just like that. So the idea here is that if I have these two forces are equal but opposite in direction, if I had to look at my resultant force from these two forces, it would be equal to 0. And because of that, it means that if I have a couple that's applied to an object, it isn't pushing it in any particular direction. There's no push. There's only a rotational force. So from our sum of the forces equals 0, we end up with no translational force is the more technical term, right? Only rotational. All right, so taking a look at this diagram that I have here, let's say that I wanted to sum the moments about this origin point O. And I would see that, we know a moment is a force times a distance, or r cross f. So this would be the radial arm out to point A crossed with the force, and I would add that to the radial arm out to B crossed with the negative force, because that's going the opposite direction. And I can factor out this force since I know it's equal in magnitude, and that would equal to the radial arm of A minus the radial arm of B crossed with the magnitude, or the vector, of the force. So what that really in essence is saying is that my RA and my RB can be replaced with a single R value, which is the distance between, or the distance from RB to RA. So really I end up with a final result that looks like this. The moment about point O is equal to R cross F. And this R is the distance between, or the, I guess the radial arm distance between those two forces. Now the reason that's kind of a cool result is it is independent of where O is. So if I had a different point over here and I had two different radial arms, it wouldn't make any difference. So once we have a moment couple, they can be applied anywhere and it has the overall same effect. Now, once again, it has to be a force times the perpendicular distance between those two forces. So another way you'll see this is that the moment is equal to RF sine theta, and that's assuming that theta, like here is shown, is between this radial arm and this F, or F times this perpendicular distance. So let's take a look at a quick example, fairly easy example of how we're using these moments. So this is my example that I have sketched out. I can see that I have these two force couples. I have or moment couples. I have the two 21 pounds, and I have 16 inches between them, and then I have these two 21 pound forces, 16 inches between them, two 12-pound forces with some unknown D. A couple things we're going to find. The first thing, let's try and find, if I just wanted to find the moment couple from the 21-pound forces. So this starts off pretty easy because what I want is, it's just a force times a perpendicular distance, and I see that the moment of the 21 pounds, or the distance between these 21 pounds, is perpendicular at 16 inches. So it's just the 21 pounds times the 16 inches, giving me something like 336 pound inches, or inch pounds, either way. For part B, let's see if we can find the perpendicular distance between the 12-pound forces if we want a resultant couple of 0. If I'm looking at that, if my resultant couple is 0, it means that my moment from two forces plus the moment from the other couple must be equal to 0. I just found that I have a 336 pound-inch moment from those 21-pound forces. So of course I have to subtract out the moment couple from the 12-pound forces, and we said that would be equal to the magnitude times the perpendicular distance. Well, that's just d equal to 0. Solve for d, and I end up with d is equal to 28 inches. Now the last thing that we're going to try and find here is, could we find this angle alpha if I were to give you a d value, and we're going to say d is equal to 42 inches, and we're going to have a resultant couple of negative 72 pound-inches. Well, similar to what we just did up above, we can add these couples together, and I end up with m1 plus m2 must be equal to this negative 72. m1 is still this 21 times 16, or 336. This m2, which is going the other direction, we can still stick with our same sign convention where we're saying that counterclockwise is positive in this case. So for our second moment for these 12-pound forces, I have 12 pounds times some kind of perpendicular distance. We'll have to figure out what that perpendicular distance is, and that's where I get this 42. Oh, hey. 42 times the sine of alpha. So there's two ways that you can think of this. One is that I'm finding the vertical component for each one of these 12-pound forces, right? Which would be 12 times the sine of alpha. Or the other way you can think of it is if I have some kind of distance, and what I need is a distance. It's going to be ugly if I try and draw it, but I need a distance that's going to be the perpendicular distance, and then that perpendicular distance would be the sine of alpha times my original distance. I'll give up on drawing that one. But I know that in total this has to equal my negative 72. Get my right color in here. So I can solve for this alpha, and I got an alpha of 54.05 degrees. So one of the cooler things about this idea of a force couple is it starts to open up these ideas of replacing forces or resolving a force into a force and the result of the couple. Let me that may have sounded very confusing, but let me write out exactly what I'm talking about here. So for instance, let's say that I have this kind of blob object here, and I'm applying a force to this object some distance away. We'll put it about here, and have some kind of force. And what we want to do is, we'll call this point O over here. What we want to do is we want to move the force to point O. And the reason we want to do that is there's actually a lot of scenarios where you can solve a problem or find the overall result of, I have an example coming up, like a twisting of an I-beam or something like that, or the net effect of the force. But regardless, what I have is a radial arm that goes from the point O out to this force. The first step would be to move this force exactly how I want to do it. So I'm redrawing the exact same scenario there, and I'm just going to add the same magnitude, same direction force where I want it. In order to do that, I have to add one that is equal and opposite. So this would be a negative F going the other direction. So I haven't actually altered my object, meaning if this object originally had some kind of force that was pushing it, looks like up and to the right, we still have the same magnitude of force pushing it up and to the right, because those other two forces are canceling each other out. So those other two forces don't actually do anything if I add those two in there. But what I notice after I do that is now I do have two equal and opposite force vectors, or a couple, right? So finally what I can do is my last step would be, I had this first point over, well, a little up further over there, but it's in essence going away, and I end up with just this one force F, but instead of that force couple, I'm going to represent that just as like some kind of moment. So I would have some kind of moment that's wanting to spin around, or I don't know, actually it would probably be going around a different axis or something like that, but But that's the general idea. And let me show you with an example. Hopefully clear it up a little bit. So for this example, I have an I-beam. I have a 260 pound force being applied at point A. And what we're looking to do is to replace the 260 pound force with an equivalent force couple at point C. So the way we do that is that the first thing that I'm going to want to do is find out what my current moment is at C, because that's what has to stay the same after I move that 260 pound force there. So let's see, the first thing I did is I found the length of this AB vector, and I found that AB is equal to 6.5 inches long. So the reason I did that is then I can break this force into components as we've done before. This is 6.5, this is 2.5, and this is let's see, it's 2 up, so this would be what, 6, right? And this is my 260 pound force. So with that in mind, if I do sum of my moments about C, what I have is this 260 pound force times 2.5 over 6, which is my horizontal component, and then its lever arm would be about point C, would be 4. And that all, we're still sticking with that same sign convention. Let me scoot this down just a little bit to give myself a little bit more room, because I still have my other component to go, which is in the negative or clockwise direction. I have the vertical component, 6 over 6.5, and its lever arm of 2.5. And if I do all that, I end up with negative 200 pound-inches, or what that really means is I have 200 pound-inches in the clockwise direction. So that's what the moment is from the 260 pound force. About point C, it's causing it want to spin around with this 200 pound-inches. So in essence, the result would be, if I were to redraw, oh, I didn't plan on doing this, but let's try and do this quickly to see what it looks like. If I were to redraw this I-beam, my end result would have a force that's applied at point C that's equal to this 260. It's the same magnitude as before. That means the I-beam is being pushed down and to the left with the same 260 pound force. And then there's also a moment that we're going to apply to that point, which is equal to this 200 pound-inches. So that's what my I-beam would look like afterwards. So like I said, now why would we want to do something like this is, in the real world I might have a scenario that, you know, that this I-beam actually has a force of this 260. And what I want to know is if this is, like, say, the center of the I-beam, which it is right at the center, right? If this is the center of the I-beam, and the I-beam feels like it's being twisted in a way, or torqued in a way, and also pushed down. So that's when we'd look at the shear stresses and the bending stresses, and then also the torque on that I-beam to get the right size, so we don't actually kill people. So that's what I have today, and thanks for watching. Talk to you soon.